Right now, I want you to imagine the hottest thing you have ever felt. Perhaps it was the accidental brush of a fingertip against a red-hot stove, the searing, instantaneous recoil of your nerves screaming in protest. Maybe it was the oppressive, suffocating wall of air that hits you when you open an oven door, or the humid, sticky, heavy blanket of a tropical heat wave that makes the air feel like soup. Take that sensation, that vibration of atoms against your skin, and hold it in your mind. That pain, that discomfort, is nothing. It is a rounding error. It is barely a vibration in the grand, frozen silence of the cosmos. We are creatures of the temperate zone. We live in a terrifyingly narrow band of thermal existence. If the temperature drops just a few dozen degrees, our blood crystallizes and our cells shatter like glass. If it rises just a few dozen degrees, our proteins unravel, our enzymes cook, and we cease to function. We are fragile biological machines, obsessed with the cold. We fear the winter. We fear the heat death of the universe, the entropy, the slow fade into eternal dark. We talk endlessly about absolute zero, the theoretical floor where all motion stops, the bottom of the thermometer. We think we understand the cold. It is a limit. It is a wall. But we rarely talk about the ceiling. We assume that heat is infinite. We assume that if you have enough energy, enough fuel, enough power, you can just keep heating the universe forever. You imagine that you can turn the dial up and up and up, past the melting point of lead, past the burning point of hydrogen, past the seemingly limitless fires of the Big Bang, into infinity. You are wrong. There is a ceiling. There is a specific, calculated number, a hard limit written into the source code of reality. There is a temperature so high that physics itself simply gives up. It doesn't just burn, it breaks. Geometry unravels. Gravity becomes nonsense. The fundamental forces that hold you, the Earth, and the atoms of your body together dissolve into a chaotic foam of impossibility. This is not a story about fire. This is a story about the breaking point of the universe. This is a story about the absolute hot. And to understand it, to truly grasp the horror of what happens when we push reality too far, we have to leave the safety of the Earth. We have to climb the ladder of temperature, rung by terrifying rung, until we reach the top. Let's begin the ascent. First, we must dismantle your understanding of what heat actually is. To a physicist, heat is not a substance. It is not a fluid that flows from a hot coffee cup into your hand. Heat is motion. It is the chaotic, violent jittering of atoms. The hotter something is, the faster its particles are moving. In the air around you right now, the nitrogen and oxygen molecules are bouncing off your skin like billions of tiny microscopic bullets, traveling at roughly 1,000 miles per hour. That bombardment is what you feel as room temperature. If we cool them down, they slow. At absolute zero, they stop. The silence is perfect. But if we speed them up, things get violent. Let's turn the dial. We leave the comfortable 70 degrees Fahrenheit of your living room. We bypass the 212 degrees of boiling water, where the violence of the molecules is strong enough to tear liquid apart into gas. We ascend past the melting point of lead, past the lava flows of primordial Earth. We arrive at the surface of the Sun, 5,500 degrees Celsius. This is the visual anchor you are used to, a blinding white-hot plasma. But in the grand scheme of the universe, the surface of the Sun is lukewarm. It is practically chilly. You could replicate this temperature in a high-end industrial welding arc. We are not impressed yet. We need to go deeper. dive into the core of the Sun. Here, the weight of a star, 330,000 times the mass of the Earth, is crushing down on hydrogen atoms with such ferocity that they have no choice but to fuse. They smash together, desperate to escape the pressure, releasing screams of gamma radiation. The temperature here is 15 million degrees. At 15 million degrees, matter as you know it is gone. You're no longer dealing with solids, liquids, or gases. You're in the fourth state, plasma, a soup of stripped electrons and naked nuclei. If you were to teleport a single pinhead of material from the Sun's core to the surface of the Earth, the heat radiating from that tiny grain would kill every living thing within 100 miles instantly. It wouldn't just burn them, the radiant energy would vaporize the water in their bodies before their nerves could even register the heat. But we are still at the bottom of the ladder. 15 million degrees is a rounding error. The universe has forged engines far hotter than our polite, middle-aged yellow star. Let's look at a supernova. When a massive star, a distinct behemoth 20 times the size of our Sun, reaches the end of its life, it runs out of fuel. The engine stops. The outward pressure that held the star up against gravity vanishes. In a fraction of a second, the entire star collapses inward. It falls in on itself at 25% the speed of light. It crashes into its own core. The resulting shockwave generates temperatures of 3 billion degrees. At 3 billion degrees, the violence is hard to comprehend. We are approaching a realm where the thermal energy is so intense that it begins to interfere with the stability of atomic nuclei. But we can go higher. We have built machines on Earth right now buried beneath the borders of Switzerland and France that can put a supernova to shame. Inside the Large Hadron Collider, we take protons, the tiny positively charged hearts of atoms, and we spin them. We accelerate them around a 17-mile ring of superconducting magnets until they are traveling at 99.9% of the speed of light. And then we smash them together. For a fraction of a second, in a space smaller than an atom, we recreate the conditions of the universe just moments after its birth. The temperature in that collision point reaches 5.5 trillion degrees Celsius. 5.5 trillion. It is a number so large it loses meaning. Let me give you a scale. If the core of the Sun were the size of a single grain of sand, the temperature inside the Large Hadron Collider would be a mountain towering over it. At this temperature, protons and neutrons melt. The basic building blocks of matter dissolve into a primordial slurry called quark-gluon plasma. This is the stuff the universe was made of before it cooled down enough to allow matter to exist. This is the soup of creation. We have touched it. We have created it in a lab. And yet, even at 5.5 trillion degrees, reality is holding together. The laws of physics are sweating, they are straining, but they are not breaking. The grid is intact. We have not hit the ceiling. To find the ceiling, we have to look backward. We have to rewind the clock of the cosmos. We have to go back to the first second. The Big Bang was not an explosion in space. It was an explosion of space. It was a moment of infinite density and infinite heat expanding outward. If we look at the universe when it was just 1 second old, the temperature was 10 billion degrees. If we go back further to when the universe was a fraction of a second old, specifically 10 to the power of negative 35 seconds, we enter the inflationary epoch. The temperature is 10 to the power of 27 degrees. That is a 1, followed by 27 zeros. At this heat, the forces of nature are unrecognizable. Today, we see four distinct forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. They are the rules of the game. But at these temperatures, the rules change. Electromagnetism and the nuclear forces melt together into a single, unified superforce. We don't fully understand the physics here because we cannot replicate it. It is too hot for our math. But we are still not at the limit. We are still climbing. You might be asking, why is there a limit? If heat is just motion, why can't we just make things move faster? Why can't we pump infinite energy into a particle and get infinite heat? Here is the catch. Here is the uncomfortable truth that ruins the fantasy of infinite power. Einstein gave us a speed limit. Nothing can move faster than light. Remember, temperature is kinetic energy. It is speed. As you heat a particle, it moves faster. But as it approaches the speed of light, it hits a wall. You cannot make a particle go faster than c, 299,792,458 meters per second. The universe forbids it. So what happens when you keep pumping energy into a particle that is already traveling at 99.9999% of the speed of light? If it can't go faster, where does the energy go? This is where the horror begins. This is where the universe starts to play a very dangerous game with us. Einstein also told us that energy equals mass times the speed of light squared, ES-mc2. Energy and mass are interchangeable. They are the same currency. When you add energy to a particle that cannot go any faster, that energy doesn't disappear. It converts. It becomes mass. The particle gets heavier. Imagine you are heating a gas. The atoms fly faster and faster. They hit the light speed barrier. You keep heating them. They don't speed up anymore. Instead, they start to gain weight. They become bloated, monstrous versions of themselves. Each atom begins to swell with relativistic mass. Now, recall what mass does. Mass creates gravity. Usually, atoms are too light for their gravity to matter. But at these extreme, godlike temperatures, the atoms become so heavy, so gorged on energy, that their own gravitational pull becomes significant. They start to pull on each other, not with chemical bonds, but with raw gravitational force. We are now approaching the absolute hot, the theoretical ceiling. It is called the Planck Temperature. The number is 1.42 times 10 to the power of 32 degrees Kelvin. 142,000 degrees. This is not just hot. This is the temperature at which the wavelength of light emitted by the heat becomes smaller than the smallest possible distance in the universe, the Planck length. Physics tells us that the universe is pixelated. There is a smallest possible unit of distance. You cannot cut space into smaller pieces than the Planck length. It is the resolution limit of reality. When you heat something to the Planck temperature, the energy is so violent, the vibration so fast, that the wavelength of the radiation it produces tries to become shorter than the pixel size of the universe. The math demands a wavelength smaller than existence allows. And something else happens, something far more terrifying. Remember the mass? At the Planck temperature, the energy density is so high, the particles are so heavy with relativistic mass, that every single point of space becomes a black hole. This is the anomaly. This is the breakdown. If you try to heat an object above the Planck temperature, you don't get a hotter object. You get a Kugelblitz, a black hole formed from radiation. The energy turns into a prism. The object collapses inside its own event horizon. The universe effectively says, no. It censors you. It hides the region of space that disobeyed the laws of physics behind a wall of darkness that nothing can escape. You cannot make the universe hotter than this, because if you try, the universe simply deletes that section of space-time. It removes it from the board. The Planck temperature is the firewall. It is the fail-safe mechanism designed to prevent us from seeing the naked singularity, the chaotic code underneath the simulation. But recently, some physicists have begun to whisper that we might be wrong. They suggest that the ceiling might be much, much lower. They suggest that long before we reach the Planck temperature, something else breaks, something stranger. They call it the Hadron temperature. And if they are right, the universe doesn't just turn into black holes when it gets too hot. It changes phase. Just as ice melts into water, space-time itself might melt into something else. We have assumed for centuries that space is the empty stage upon which the drama of the universe plays out. We assume the stage is fireproof. We assume the stage is indestructible. But what if the stage is made of ice? And what if we are holding a match? This is the question that keeps cosmologists awake at night. Because if space can melt, if the vacuum can boil, then we are living on very thin ice indeed. And the terrifying part is, we might have already seen the bubbles forming. To understand why the fabric of reality might melt, you have to stop thinking of nothing as empty. Go to the darkest, emptiest corner of deep space. Remove the stars. Remove the gas clouds. Remove the stray atoms. Shield it from radiation. Get it down to absolute zero. What do you have left? You think you have nothing. You think you have a void. You are wrong. You have a boiling, frothing ocean. Quantum field theory tells us that empty space is not empty. It is filled with fields, invisible grids that stretch across the entire universe. The electromagnetic field, the electron field, the Higgs field. These fields are like the surface of a drum. Even when no one is hitting the drum, the skin is still tight. It still has tension. It still vibrates. In the vacuum of space, particles are constantly popping into existence and destroying each other. Pairs of virtual particles, matter and antimatter, borrow energy from the vacuum, snap into reality for a nanosecond, and then collide and annihilate back into nothingness. It is a constant, violent foam. The silence of space is actually a roar of quantum fluctuation that we just can't hear. Now, imagine heating that vacuum. Think of boiling water in a pot. You add heat. The water molecules get excited. They move faster. Eventually, they hit a critical point, a phase transition. The liquid water can no longer hold its structure. The bonds break. The water turns into steam. It changes its fundamental nature. Physicists believe that the vacuum of space, the very field that defines the laws of physics, can also undergo a phase transition. This is where the Hadron temperature comes in. In the 1960s, a physicist named Rolf Hagedorn was looking at the soup of particles created in high-energy collisions. He noticed something strange. As you add energy to this soup, the temperature goes up, just as you'd expect. But eventually, the temperature stops rising. You keep pumping energy in, but the thermometer doesn't budge. Where does the energy go? It goes into creating new particles. The heat stops making the particles move faster and starts making more particles. It's like trying to boil a pot of water, but instead of the water getting hotter, the pot just spontaneously fills with more water. Hagedorn calculated that there might be a limiting temperature for hadronic matter, the stuff we are made of. A point where you can't make matter hotter, you just make the universe denser. A runaway explosion of mass. But modern string theory takes this a step further. It suggests that if you hit this specific temperature ceiling, you trigger a phase transition in the vacuum itself. You melt the drum skin. What happens then? We lose the math. But the theories suggest that at this temperature, the fundamental forces might decouple. The rules of gravity, electromagnetism, and the nuclear forces are rewritten. The constants of nature, the speed of light, the charge of an electron shift. If you were standing in a region of space that underwent this transition, you wouldn't just burn. You would cease to be biologically or chemically possible. The atoms in your body rely on the electromagnetic force to hold their electrons in orbit. If that force changes, or if the vacuum strength that determines the mass of the electron shifts, your atoms don't just fall apart. They stop being atoms. You dissolve into a mist of unrecognizable exotic matter. But that's just a local problem. That's just you dying. The true horror is what happens to the rest of the universe. We call it vacuum decay. Imagine the universe is a ball sitting in a valley. The valley represents the energy state of the vacuum. We are at the bottom of the valley, stable and comfortable. We call this the false vacuum. It feels solid. It feels permanent. But what if there is a deeper valley right next to us? A true vacuum with a lower energy state. A massive burst of heat, like the temperatures we are talking about, could kick the ball over the hill. It could push a tiny bubble of space from our current stable state into the lower, true state. This bubble of new physics would appear instantly. And because it is at a lower energy state, it is more stable than the space around it. It wants to grow. It would expand at the speed of light. There is no warning. There is no siren. You cannot see it coming because it is moving as fast as the light you see with. One moment, you're looking at the stars. The next moment, the wall hits you. Inside the bubble, the laws of physics are different. Maybe chemistry is impossible. Maybe matter cannot form. Maybe it's just a void of pure, crushing gravity. We don't know. All we know is that it deletes the universe we understand. It is a spherical shell of erasure, expanding outward, devouring galaxies, rewriting the source code of reality, and leaving nothing but silence behind it. And once it starts, it cannot be stopped. Now, let me make this personal. Let me take this out of the abstract realm of diagrams and equations and put it in your backyard. We are playing with fire. We are building machines to reach higher and higher temperatures. We want to understand the Big Bang. We want to unlock the secrets of the beginning. But every time we smash particles together at near light speeds, we are essentially knocking on the door of the vacuum. We are tapping the glass. We assure ourselves that it's safe. We say, cosmic rays hit the Earth's atmosphere with far more energy than our particle colliders, and the Earth hasn't been destroyed. This is true. Nature has been running these experiments for billions of years. But there's a chilling concept in probability called the Great Filter. It asks, why is the universe so quiet? There are billions of stars, billions of planets. Life should be everywhere. We should hear radio signals, we should see Dyson spheres, we should see galactic empires, but we see nothing. Just dead rocks and silence. The Great Filter suggests that there is some hurdle, some trap that civilization hits before it can spread to the stars. A step in evolution that is almost impossible to survive. Maybe the filter isn't nuclear war. Maybe it isn't a plague. Maybe it isn't an asteroid. Maybe the filter is physics itself. Perhaps every intelligent civilization eventually discovers how to manipulate energy. They discover the atom. They discover fusion. They build colliders. They chase the absolute hot. They want to know the mind of God. And maybe, just maybe, one day they succeed. They build a machine that reaches the critical temperature. They create a tiny microscopic bubble of true vacuum in a lab. It would look like a flash of light. And then, the planet is gone. Then, the star system. Then, the galaxy. A silent, expanding sphere of death that cleans the universe of the civilization that was foolish enough to light a match in a room full of gasoline. This theory solves the Fermi paradox, the question of where is everybody, in the most horrifying way possible. They are gone because they got too smart. They are gone because they touched the ceiling. The universe is a graveyard of empty galaxies, sterilized by the pursuit of knowledge. And we are currently racing, with excitement and pride, toward that same finish line. But there is a twist to the heat death, a way that the heat doesn't just destroy us, but traps us. Let's go back to the black hole limit, the Kugelblitz. If we cannot trigger vacuum decay, if the universe is stable, we still have the problem of the Kugelblitz. As a civilization grows, it uses more energy. We started with fire, then steam, then oil, now nuclear. Our energy consumption grows exponentially. A Soviet astronomer named Nikolai Kardashev ranked civilizations by their energy use. A Type 1 civilization controls all the energy of its planet. A Type 2 controls its star. A Type 3 controls its galaxy. We dream of becoming a Type 3 civilization. We dream of spanning the Milky Way, harvesting the energy of billions of stars, computing at the speed of light. But thermodynamics is a cruel master. Every bit of energy you use eventually turns into waste heat. Your car engine gets hot. Your computer fan spins to blow away heat. Even your brain produces heat as you think. You cannot destroy energy, and you cannot use it with 100% efficiency. The entropy must increase. If we cover the galaxy in computers and cities and starships, we will generate heat. An unimaginable amount of heat. If we cage a star to harvest its energy, the cage heats up. If we build a supercomputer the size of a planet, it glows. Eventually, a Type 3 civilization might generate so much waste heat that the galaxy itself begins to cook. We wouldn't need a collider to reach the danger zone. Our mere existence, our daily commute, our internet servers, our very infrastructure would raise the background temperature of the galaxy. We would be trapped. If we generate more power, we cook ourselves. If we stop generating power, we stagnate and die. We would have to design our entire civilization not around exploration or art or conquest, but around cooling. We would become slaves to the radiator. We would have to flee to the edges of the galaxy, to the dark, cold voids, just to dump our waste heat. We would be huddled in the dark, afraid to turn on the lights, because the lights make it too hot to breathe. This is the heat death in reverse. Not a slow freezing, but a frantic, claustrophobic suffocation. A universe where intelligence becomes a cancer that burns its own host. And the scary part? When we look at the universe with our infrared telescopes, scanning for the waste heat of alien empires, we see nothing. No Dyson spheres, no galactic radiators, no vast clouds of warm exhaust. Does this mean we are alone? Or does it mean that everyone else learned the lesson the hard way? Or Is there something even bigger out there? Something that regulates the temperature? We have looked at the ceiling of temperature. We have looked at the breaking point of the vacuum. But there is one final horror, one final implication of the absolute hot that changes everything about how we perceive time and the future. It has to do with the beginning, and it has to do with the cycle. If the universe began in a state of absolute hot, a singularity of infinite temperature, and is cooling down, what happens if it decides to heat up again? We assume the Big Bang was a one-time event, a starting gun. But in physics, many processes are reversible. There is a cosmological model called the Big Crunch. It is less popular now, overshadowed by dark energy, but it still haunts the equations. It suggests that gravity might eventually win. The expansion of the universe could slow, stop, and reverse. The galaxies would rush back together. The stars would collide. The background radiation would shift from microwave to visible, to ultraviolet, to gamma. The sky would turn white. The universe would contract. And the temperature would rise. We would be forced back up the ladder. We would watch the oceans boil, the planets melt, the stars vaporize. We would be compressed back into the plasma, back into the quark soup, back into the energy. We would return to the absolute hot. And maybe, just maybe, this has happened before. Maybe this universe is just one breath in an eternal cycle of heating and cooling. A cosmic lung, breathing in fire and breathing out ice. And if that is true, then we are not living in a unique moment. We are just recycled ash from the last time the oven was turned on. We are trapped in a loop of incineration. But there is a way out, or at least a way to see the bars of the cage. To understand the true structure of this thermal prison, we have to look at the far, far future. We have to look at what happens when the universe tries to cheat the system. We likely won't get the fire. Despite the terrifying possibility of the Big Crunch, the universe collapsing back into a singularity of absolute hot, the evidence we have gathered points to a different, colder fate. We are seeing the galaxies speeding up as they move away from each other. Dark energy is pushing the cosmos apart. The rubber band isn't snapping back, it is stretching until it loses all elasticity. This means we will not end in a blaze of glory. We will not return to the Planck temperature. Instead, we are marching slowly, inevitably, toward the absolute zero. But do not be comforted by the cold. The cold brings its own kind of madness, a horror far more psychological than the physical destruction of the heat. To understand the end, we have to understand what we are. We are heat engines. You, the Earth, the Sun, the galaxy. We are all just temporary anomalies in the flow of entropy. We exist because there is a difference between the temperature of the stars and the temperature of the void. We live in the gradient. We feed on the flow of energy from hot to cold. But a gradient cannot last forever. Imagine a cup of hot coffee sitting in a sealed, insulated room. At first, the coffee is hot and the air is cool. There is activity. Steam rises. Currents of air move. But give it an hour. The coffee cools down. The air warms up. Eventually, they reach the same temperature. The flow stops. The movement ceases. The coffee is dead. The universe is that room. Currently, we are in the stellar era. The coffee is still hot. Stars are burning hydrogen, creating islands of high temperature in a freezing ocean. But the fuel is finite. In about 100 trillion years, the last star will be born. It will be a small, red dwarf, barely sipping its fuel, trying to stay alive in the encroaching dark. When it dies, the lights go out, permanently. This is the heat death. It is a misnomer. It is not a death by heat, it is the death of heat. It is the state of maximum entropy. The universe becomes a uniform bath of useless, low-level radiation just a fraction of a degree above absolute zero. No. Information can be processed. No thoughts can be formed. No time can be measured. Because time requires change, and in the heat death, nothing ever changes again. But here is where the story of the absolute hot comes back to haunt us in a way you usually only find in nightmares. We talked about the ceiling of temperature, the Planck temperature. We talked about how high energy creates chaos. But quantum mechanics tells us that even in the absolute void, even in the heat death, there is never zero energy. There are always fluctuations, tiny random spikes of heat. If you wait long enough, and in the heat death, you have eternity, strange things start to happen. The second law of thermodynamics says that entropy always increases. Order inevitably turns into disorder. A sandcastle turns into a pile of sand. A pile of sand never spontaneously turns into a sandcastle. Almost never. It is a statistical law, not an absolute one. There is a non-zero probability, a tiny laughing fraction of a chance, that if you shake a box of sand for 1 trillion years, the grains might accidentally land in the shape of a castle. Now apply this to the dead universe. The cosmos is a box of particles bouncing randomly in the dark. For eons, nothing happens. But given infinite time, eventually a random fluctuation of heat will occur. Particles will collide in just the right way to lower entropy for a split second. It might just be a flash of light. It might be a single atom forming. But if you wait longer, unfathomably longer, you might get a fluctuation large enough to assemble a molecule. Wait longer, and you might get a protein. And if you wait a length of time that cannot be written down with human numbers, the random thermal fluctuations of the void could, theoretically, spontaneously assemble a human brain. We call this a Boltzmann brain. This is the ultimate horror of the heat death. It suggests that in the infinite timeline of the future, there will be far more accidental minds created by random thermal noise than there ever were biological minds created by evolution. This brain would appear out of the vacuum, fully formed, complete with memories. It would have memories of a childhood it never lived. It would remember seeing a sun that burned out trillions of years ago. It would remember listening to a script about the temperature of the universe. And then, an instant later, the fluctuation would destabilize and the brain would dissolve back into the void. This leads to a terrifying question. Are you a biological entity, born of billions of years of evolution on a planet orbiting a star? Or are you a Boltzmann brain? Are you actually a momentary fluctuation in the deep, freezing future, hallucinating this entire life, hallucinating the screen in front of you, hallucinating the sensation of your own hands, just milliseconds before you dissolve? You cannot prove you aren't. Statistically, it is more likely that you are a hallucination in the void than a real person. Because the era of real life is a blink of an eye compared to the eternity of the void. We are the rare ones. The dead universe is the norm. This is the legacy of heat. It creates the illusion of reality. But let's step back from the solipsistic cliff. Let's look at the physical reality of the absolute hot one last time. Because there is a theory that suggests the heat death is not the end, but the trigger. We know that the Big Bang started with a singularity of infinite heat. We know that the universe is expanding and cooling. Sir Roger Penrose one of the greatest physicists of our time, proposed a model called conformal cyclic cosmology. It relies on a strange quirk of physics. Scale requires mass. If you have no mass, you have no sense of time or distance. A photon, a particle of light, does not experience time. From a photon's perspective, the moment it is emitted from a star and the moment it hits your eye a million years later happen at the exact same instant. It also doesn't experience distance. To a photon, the universe has no size. In the far, far future, after the black holes have evaporated, a process that takes googles of years, the universe will be empty of mass. All the protons will have decayed. All that will be left is photons, light. At that moment, the universe forgets how big it is. Without mass to define scale, a universe that is infinitely large and cold is mathematically indistinguishable from a universe that is infinitely small and hot. The cold, dead, stretched out void loses its meaning. The geometry resets. The infinite expansion of the old universe becomes the singularity of the new one. The absolute zero becomes the absolute hot. And the Big Bang happens again. It is a phoenix cosmology. We are born from the ashes of the previous ion. The heat that warms your face today is the recycled gravity of 1 trillion dead ghosts from the universe before ours. And one day, we will become the fuel for the next iteration. So, where does that leave us? We are suspended between two fires. The fire of the beginning, the Planck temperature that forged the laws of physics, and the potential fire of the end. Whether it be a vacuum decay that burns the slate clean, or a cyclic restart that recycles our essence. We are creatures of the Goldilocks zone. Not just in space, orbiting at the right distance from the sun, but in time. We live in the brief, flickering moment between the fire and the ice. We live in the only time in the history of the universe where life is possible. Before us, it was too hot. Matter couldn't hold hands. After us, it will be too cold. The stars will be gone. We are looking at the universe during its brief, brilliant fireworks display. We think this is normal. We look up at a night sky filled with stars and assume this is how the universe is. It is not. This is a temporary anomaly. The default state of the universe is dark. The default state is cold. The default state is dead. We are the interruption. We are the glitch. So, when you ask, how hot can the universe get? You are really asking, how alive can the universe be? Heat is motion. Heat is change. Heat is the violence that allows things to exist. We shouldn't fear the absolute hot. We should miss it. We are moving away from it every second. Every day, the universe gets a little bigger, a little colder, a little darker. We are sliding down the slope of entropy. We are cooling embers, drifting apart in the dark. So the next time you feel the sun on your skin, or the warmth of a fire, or the heat of another human being, remember what you are feeling. You are feeling the echo of the Big Bang. You are feeling the rare, precious vibration of a universe that is still, for a little while longer, alive. Don't take it for granted, because the forecast for the rest of eternity is freezing, with a chance of nothingness. The fire is going out. Enjoy it while it lasts.